Chapter 7 covers the mechanical properties of materials. Now, much of this chapter will have been covered in a strength of materials course or a mechanics of materials course, starting off with stress and strain. Stress is the force over area. Strain is the percent deflection of a material in tension or compression or in shear. And why are they used instead of load in deformation? Very important question. We'll get into it and use them extensively. Elastic behavior and plastic behavior. Elastic behavior is the stretching, whereas plastic behavior is the permanent deformation. How do these materials deform? Which ones deform most or least? What are their general characteristics based on materials and their atomic structures? Toughness and ductility are material properties that we can use to create certain effects in certain situations, and we can measure them and compare them from one material to another. Elastic deformation can be characterized on even on a atomic level. Here you see the layers and the planes that are making up this atomic structure, and initially it looks like this. Then we put a load on. The bonds between the atoms are going to stretch. So you see the space. That space is reflected in a large scale deflection. But once we reduce that load and take it off, an elastic deformation, once it's unloaded, it will return back to the original position. Elastic means reversible. It'll just go up and down this particular slope here. Force versus deflection. Put more force on, you get deflection. You take it off, you get zero. Now, some materials will behave in a nonlinear elastic method, but the same concept still applies. You put the load on, and it will deform a certain amount for a certain force, and then you take the load off, and it will come back to its original position. In plastic deformation, we start off again with the atoms lined up in their crystalline fashion, but then we put enough of a load on it so that they don't just stretch, but the bonds actually break and the planes shear. So we start out with this set of atoms in this position. They end up shifting down into this position, and this set here shifts here. So once we take the load back off, these planes have still sheared, and they're going to stay in that position. So there's a resulting deformation. That's plastic deformation. It's permanent. Now, in this situation, when the force is still on it, we have both elastic and plastic. When we take the load off, there is some residual deformation that's permanent. Engineering stress is referred to as engineering stress versus true stress. The actual area does change, but most of the time we are considering the original area. So the tensile stress is referred to and represented by the Greek letter sigma, and it refers to a force that is distributed over an area, and this force is perpendicular to this area. So the stress is the force divided by the area, and it has units of pounds per square inch or newtons per square meter, and this newtons per square meter is a Pascal. A newton per square millimeter is a megapascal. The Pascal is kind of a small stress, so often we'll be dealing with megapascals, sometimes even gigapascal. The next type of stress we're going to consider is shear stress, represented by the Greek letter tau, and the shear stress comes about from a force here that is parallel to the area of interest. So here's a shear force, and it's parallel to this area here. And again, shear stress is also force over area. The question is the direction of the force with respect to the area. And it has the same units as tensile stress. Tension is a type of stress where the forces are trying to pull apart at a particular cross-section of interest. So this is a normal stress represented by sigma, equal to force over the area, and can be shown in this cable on this ski lift. Shear stress is the type of stress in a drive shaft. So as this drive shaft is twisting this circle around, the torsion in that drive shaft is causing a twisting motion and looking to shear, cut this material. Now, in order to have static equilibrium, we also have shearing stresses on the vertical faces of this small element. Also on this ski lift, you'll see this member. Now, there's a lot of tension on this cable seeking to pull this whole tower down. So we have another member here that is holding it up. This member is in compression. For a couple other examples of compression, we have this rock is loading this rock and trying to crush it. So this is also a normal force, so it's represented by sigma. It's got the force divided by the area. This column is also in compression from the load up above and the support down below. More complicated states of stress include a pressure tank, where there is a longitudinal force trying to, shall we say, move the cap off. So it's trying to cut it down the middle, and there's also a circumferential stress trying to unzip it along the edge. So this has two normal forces on it. A fish underwater has hydrostatic compression. That's stress from all three directions, X, Y, and Z. Engineering strain is calculated by looking at the deflection of a member under load. So here we have a member that was in the black rectangle, was loaded, now is the green rectangle. It is both longer and narrower after the load. The length deflection, in this case it's this is the axial deflection, is this delta divided by the original length. The lateral strain is the change in the width or the diameter. So strain is represented by the Greek letter epsilon, and it's equal, the lateral strain is equal to the change in width by the original width. Now it has a minus sign because it's actually getting smaller. There's also a shear strain, so where we have a shear force represented by these red arrows, we can calculate the shear strain. It is actually an angle, not a deflection. It's an angle calculable by the inverse tangent of this change in x over the height, in this case y. No matter what, strain is always dimensionless. Notice that this is a length divided by length, and this is a simply an angle, maybe either in radians or degrees. Now that was engineering stress and strain. True stress and strain is force for stress divided by the area at the moment of measurement. So the area actually changes over the course of the strain, and we can use these values to calculate what the actual stress is going to be. And the strain is equal to the natural log of the length over the original length. So the true stress and strain is a little more difficult to calculate, but still can be important in certain situations. Notice how the true stress always is going up, whereas the engineering stress actually goes down after a certain point. That's because the area for many materials will get smaller. It will neck, as we'll see in a couple of moments, and the area will get smaller while the force goes down because the area is smaller. But we don't calculate the new area, we only calculate the force. True stress, we consider the change in area as well, and the force may go down, but the area goes down even faster. That's why our stress actually goes up. The force may go down, but the area goes down even faster. Here's an example very similar to what we have in our lab. We have an extensometer that measures deflection, and the load cell measures the actual force. As the crosshead moves, in our case, crosshead moves up, the specimen will get longer and narrower, and we can measure all of those. This is a typical specimen that we have in our lab, and the diameter is usually right around 1/2 inch, and our gauge length ends up being about 2 inches, and we make our calculations based on this gauge length, not on the overall length. So why do we use stress and strain instead of force and deflection? Well, let's look at the pros and the cons. For force and deflection, the pros are they're easy to measure. As the previous diagram just showed, that's what we measure. We measure the force and the deflection. It's easy to understand as well. We understand weight, we understand length. The problems are that it is sample specific. The stress and the strain will change with varying geometry. So if I've got a longer sample of the same material, it's going to change my values. If I've got a larger diameter or otherwise a different cross-section, a larger or smaller cross-section, our stress and strain will change, or our force and deflection will change, but even if it's the same material. So the force and deflection are not representative of the material. If we use stress and strain, which is force per unit area, and deflection per length, notice that this is force per unit area. That's 2 of the dimensions, and length is the 3rd dimension. So we're just normalizing our performance of our material with respect to geometry. So the pros on this is that it's not sample specific. If you used a 1/2 inch diameter versus a 1/4 inch diameter of the same material, you should end up with about the same stress and strain curve. It's representative of the material, and they're really not difficult to calculate, just using the areas. And the stress and strain are more versatile and definitely more useful. The cons of the stress and the strain is that they are more difficult to measure, so we don't measure them. We use force and deflection and then do the calculation. and they're a little bit more complicated, but nothing that we can't handle. A couple more elastic properties that we should discuss is the modulus of elasticity. Now, as we load a specimen and it exhibits a linear elastic curve, there is a certain slope to it, and that slope is the change in stress over the change in strain. And this is a material-specific property referred to as the modulus of elasticity. It's just the slope of stress versus strain in the elastic region. Sometimes it's also known as Young's modulus. Hooke's law is a restatement of this calculation. It says that stress is equal to the modulus of elasticity times the strain. And this is very helpful and useful when working within this linear elastic range. The suggested problems for this section are problems 2, 3, 4, and 5. Here's problem 7.4 worked out, where we are given a yield stress, initial length, area, and Young's modulus, and asked to calculate the force at which this will reach its maximum elastic limit. And just rearrange this equation and we can calculate that. There's also an explanation of how 1 megapascal is equal to 1 Newton per square millimeter. The second part asks what the final length of this sample is. To accomplish this, we take the Hooke's law and look at the definition of strain, which is the change in length over the original length. Rearrange the equation to find that change in length, and then just add it to the original length. As we continue to look at a variety of mechanical properties, Poisson's ratio is next on our list. Poisson's ratio is represented by the Greek letter nu and is equal to the negative of the lateral strain over the axial strain. Remember, the lateral strain is the strain that occurs along the cross section that's perpendicular to the direction of loading. The axial strain is along the direction of loading. So it's indicating how much it gets thinner versus how much it gets longer. The minus sign is placed here because one of these two, depending on whether it's in tension or compression, will get smaller. Hence it will be negative. That will cancel out with this negative. So Poisson's ratio will end up being positive. Here are some sample values between metals, ceramics, and polymers. Ceramics are much less likely to stretch their bonds compared to metals, and especially compared to polymers. The units of Poisson's ratio are dimensionless, as it is a dimensionless value over a dimensionless value. The slope of the stress-strain plot is the elastic modulus in the elastic region, but it indicates whether the atomic structures are strongly bonded to one another or weakly bonded. So if it's a sharp slope, they're strongly bonded. If it's a shallow slope, they're weakly bonded. There's also a shear modulus, which is analogous to the elastic modulus. So just as normal stress is equal to the elastic modulus times the elastic strain, shear stress is equal to the shear modulus times shear strain. So in a simple torsion test where you put a cylinder under a torque load, you'll see that the angle will go up linearly with the stress. The bulk modulus is similar in that it is a modulus based on volume rather than an angle or a deflection. And here are some special relationships. The bulk modulus is related to Poisson's ratio, and the elastic modulus and the shear modulus is also related to the elastic modulus and Poisson's ratio. The elastic modulus, or Young's modulus. Comparing these different materials, you'll notice that the metals are fairly high and within a certain range, going from tin all the way to tungsten. What's interesting about this class between graphite, ceramic, semiconductors is that graphite is at the very bottom end of this class, and yet diamonds at the very top end, and yet they're made of the exact same atoms, just a different structure. Polymers are all much lower on the scale, and composites and fibers run quite a long range, whether between wood all the way up to carbon, which is actually on par with the tungsten. Now, often we see in books that the Young's modulus is a constant. Say for steel it's 200 gigapascals. Well, it's actually temperature dependent. Steel can run anywhere from 200 plus gigapascals down below 150 depending on the temperature. Aluminum is more temperature dependent, tungsten less so. If we combine Hooke's law with the definition of stress, we can come up with a formula for the deflection in tension. So the deflection is equal to the force times the original length divided by the original area times the elastic modulus. If we want to calculate the lateral deflection, we use a similar relationship, using instead the Poisson's ratio and the original width. In torsion, we can use this relationship, 2 ml over pi r to the 4th times g. All of these have been used in a mechanics of materials course. Notice how we have material, geometric, and loading parameters. Change one, you'll change the deflection. Suggested problems for this section are 7.8 through 13. Here we have 7.9 worked out. It is asking us to find the original length of a test specimen that started with this diameter, ended with this diameter. We know its elastic modulus and its shear modulus, and we have the final length. We can assume that it's totally elastic. Well, we take these parameters, find our change in diameter. In so doing, we can find our lateral strain, and we have this as our definition of the axial strain. Put these together with Poisson's ratio and put them in this relationship between the shear modulus and the elastic modulus, and we solve all that for our Poisson's ratio. Taking that definition, we can solve all the way through here for our original length. That was our discussion of elastic deformation. Now, what happens when we go beyond the elastic limit and we yield. Here we have our yield point where we have both elastic and plastic deformations. If we unload it, it will go down a curve parallel to the elastic curve, but end up at a permanent deformation of strain, given right here at this location. It's a rule of thumb that this noticeable plastic deformation occurs when strain is equal to 0.002 or 0.2%. You find that value, you go up a curve that has the same slope as the elastic modulus, and when it runs into your stress strain curve, that's where your yield stress is. This yield strength is quite variable depending on the material. Notice that for metals and alloys, there's so many in a very wide range. But also notice that the graphite, ceramics, and semiconductors are very difficult to measure, likewise with composites, because they don't usually yield. By the time they're about to yield, they fracture. That can be an advantage or a disadvantage depending on how you use the material. As a sample is loaded, this graph shows what a ductile sample will look like. This is engineering stress versus engineering strain. Here's our elastic range. As the load gets higher and higher, notice how it goes from shorter and thicker to longer and narrower. Up at the top here is the tensile strength. After this point here, the material may neck, showing a reduced cross-sectional area. The force goes down ultimately to fracture. In metals, the ultimate tensile strength is when occurs when noticeable necking starts. The polymers, the polymer backbone chains are all aligned together in the direction of load, and this is the point at which they begin to break. This tensile strength is comparable for a variety of materials as well. Notice how carbon fibers are actually at the very top, well above steel. But also in the composites and fibers, wood is at the very bottom. It has very low tensile strength. Polymers are in the middle. The ceramics have a wide variety, even within the same type of material. Aluminum oxide, graphite, silicon nitride all have varying tensile strengths depending on the processing and their structures. Metals and alloys are usually fairly consistent within a small range for the material. Notice how the steel is here, it's here, it's here. It all depends on the type of steel and its processing. Ductility is a measure of the ability of a material to stretch, and stretch in a plastic sense. So it is measured often by percent elongation. How much does it stretch over its original length? And this is also not considering its stretching at the over the elastic region. That's why you have this curve coming back down here. So it only considers the plastic region. Same thing here. Notice that this material here has a larger ultimate stress, but it doesn't stretch as much. So this material may actually be preferred over a material that has a larger stress capability, because this one, assuming that it were to be in a place where things could get damaged, this one would give warning that it was going to fail, allowing people or property to be moved out of the way, what have you. This one here would simply break completely in a catastrophic manner. Another way of measuring ductility is the percent reduction of area, and this is the original area minus the final area, again over the original area. Toughness is a measure of the energy to break a unit volume of material. Notice it's per unit volume, so again we're going to use stress and strain, which are normalized to the 3 dimensions of volume. So this is the area under the curve. In this case, even though this material again has a higher tensile stress capability, it does not have much toughness. It can't take a lot of energy to break it. This material here, although it's got a lower ultimate tensile strength, continues to have the most toughness because it has the most area under the curve. It takes the most energy to break it. A polymer like this will have a very low toughness because there's very little area under its curve. This is a brittle fracture, and these are both more ductile fractures. The resilience is the ability of a material to store energy. Again, this is about energy. Now, this is storing the energy that it can give back, so that indicates an elastic capability. So it's the area under the elastic region here that it can move back on, so that it can essentially act as a spring, storing energy. To calculate it, we take the area under the curve from 0 to the strain, and this ends up with the square of the yield stress over twice the elastic modulus. Let's look at elastic strain recovery. Initially we load a material, and here is our initial yield stress. But then again, back to resilience, we unload it, comes back down. Now it'll come back down at the same slope as it initially went up, and this will be its plastic strain, and this will be the elastic strain recovery. We can load it back up again, and we have a new yield stress. If we do this often enough, this will eventually strain so far that it will fracture. Suggested problems for this section are 715, 17, and 18. For 715, I used a spreadsheet. I brought in load and length, calculated the deflection, and using the original diameter, and I calculated the original area, and was able to calculate from there strain, stress, the estimated elastic modulus for each point, and then a final estimation of the elastic modulus. the 0.2% offset yield stress, using this line as an approximation to find the yield stress around here. The ultimate tensile strength, which is right up here at about 180,000 psi. The ductility was the final strain minus the strain at yield. Then the modulus of resilience, again, the square of the yield stress divided by twice the elastic modulus. Mostly we've been considering metals. Now we're going to move on to ceramic materials. Ceramic materials are more brittle than metals, and there's a very good reason for it. If we have a metal that is just shifting a plane of atoms from one position to the next, then they are surrounded by the sea of electrons. However, in ceramic materials, they may only move by dislocations. What's more, in an ionic solid, there are very few slip systems. It's not a face-centered cubic, more than likely. So there's very few slip systems, and when an anion is moving over another anion, or cation over a cation, it resists this very much. So there are very few ways that a ceramic ionic solid is going to slip easily. So it makes it actually very difficult to test, very difficult to put into a tensile tester, as we've seen. So what we can do is make a small bar, either round in cross-section or rectangular in cross-section, and place a load in the center and see how much it deflects and at what point it breaks. This is known as the three-point bending test. This is what the stress strain or the force deflection diagram usually looks like. It goes up and it breaks. But we can calculate the slope, and we can find the elastic modulus based on the length between the two supports and the area moment of inertia of the cross section. Here's another diagram. This shows the stress can be calculated by mc over I, where m is the maximum bending moment, which is half the force times half the length. C is the distance from the center of the specimen to the outermost fiber. In this case, the rectangular case, it'll be half of d. In this case, it'll be the radius. I is moment of inertia for the cross section, which is different between the rectangle and the circle, shown here. And F is the applied load. So here is this diagram again. And this gives us some typical values for different ceramics. Notice how the modulus of elasticity is anywhere from 150% to almost 200% that of steel. Glass, though, is much lower. Suggested problems in this section are 725, 26, and 27. 25 is a problem of a three-point bending test using spinel. And with the givens that we have here, we use our stress equation, Stress equals MC over I. We can calculate our bending moment, our C, our area moment of inertia, and we put them into this equation straightforwardly, and we can calculate the stress. The second part is to calculate the deflection at the center right here. Plug that into this equation that we're given in the problem, and we get this value. One thing we have to look up is the actual modulus of elasticity of spinel. Polymers behave very differently than metals or ceramics. Metals have a lot of similarities, although they are different in some ways. Some are brittle, some are more ductile. Ceramics are almost always brittle, but polymers can be brittle, they can be extremely plastic, they can be elastomeric, and even the exact same specimen can be brittle or extremely plastic depending on things such as temperature or strain rate. The fracture strength of polymers is a fraction of that for metals, and the deformation is usually much larger. Again, very importantly, the temperature has a significant effect on a thermoplastic and its material properties. So for semicrystalline plexiglass at 4 degrees Celsius, the plexiglass is very brittle. Just go up straight and then fracture. Closer to room temperature, it will show somewhat of a curve before it fractures. At more elevated temperatures, it will definitely show yielding, and at 60 degrees C, it will continue to deform with load. If the strain rate is changed, that is, the machine that is doing the testing goes faster, then that has the same effect as decreasing the temperature. So it will cause a polymer to fracture faster and in a more brittle fashion if the strain rate is increased. Here's an example of time-dependent deformation. So a lot of the metals and the ceramics will not depend on time. You hold them at a certain force, and over time, yes, a long period of time, they will creep and relax their structures over a long period of time. Polymers, on the other hand, will relax over a relatively short period of time. So you could raise a polymer to a certain strain, but its stress will actually reduce over time because the polymer chains begin moving and continue to move to reduce the stress in the sample. This is considered stress relaxation. The relaxation modulus is a modulus of elasticity that changes over time with respect to the stress that also changes over time. This modulus changes depending on the temperature. So there's very little relaxation when the temperature is low, that is for amorphous polystyrene. For this material, as the temperature goes up, come into the glassy transition region. This transition region has a much lower relaxation modulus, so it is more likely to stretch. for this material, there's a little bit of a plateau, and then we get towards its melting point, where it becomes much more of a viscous liquid, and it simply continues to stretch no matter what. Notice how this glass transition temperature is very different for a variety of materials. So this means that at room temperatures, polyethylene, both low density and high density, are actually well within the transition region. PVC, on the other hand, will take almost the boiling of water to make it transition to this much more flexible material. And polystyrene, interestingly, is often processed with boiling water because its glass transition temperature is at the boiling point of water. The suggested problems for this section are 729, 31, 32, and 33. Problem 32 asks us to suggest schematic strain time plots for the following polystyrene materials at specific temperatures. We've got crystalline at 70 degrees Celsius, amorphous at 180, cross-linked at 180, and amorphous at 100. Now we'll need to use these two graphs. This is of amorphous, which is the same as the curve C, and this is the curve for crystalline, and B is the curve for cross-linked. Now the problem is a little confusing because it uses these curves. Now the load here that's involved is an initial load that is immediately put on, held, and then immediately taken off at time tr. These are possible strain time graphs that might be associated with the different types of materials or temperatures. So this is a load time curve, the other ones are strain time curves. So if we look at the first one, crystalline at 70 C, here's our crystalline curve at 70 C. Over here, it's way up here in the glassy area. This is where we will have a very rigid, elastic material. So when we follow the load curve, it should deform elastically, stay, and then come back elastically. That's what we have here. So a very glassy material will deform, stay deformed, and then completely recover. So crystalline at 70 degrees C would be this curve. Amorphous at 180 C, we can use this red one or go over here. At 180 C, you're going to see much more of a viscous flow. In fact, the elastic modulus here is going to be practically negligible. So it should, when it's loaded, it should just stretch and stretch and stretch and stretch and stretch, and then when the load is taken off, it should have pretty much no recovery. Well, that's what we've got here. As soon as the load's put on, it just stretches, and then when the load's taken off, it stops stretching but has pretty much no recovery. So this curve matches our amorphous at 180 C. Cross-linked at 180 C, that's B. So notice the difference between the amorphous and the cross-linked. The cross-linked will stay at about this elastic modulus, still pretty low, but it's going to act very differently at the same temperature as the same material, polystyrene. This one just happens to be cross-linked. So because it's cross-linked, the polymers are not going to slide with respect to each other. They're not going to deform in the same way as the uncross-linked material, the amorphous material. So when the load is put on, it's going to have an initial elastic load, and then it's going to stretch somewhat. And then when the load is taken off, it's going to come back elastically. So where do we see that? That's this curve. So it has an elastic deformation first, and then it stretches plastically for a time, then the load's taken off, and the strain, the elastic strain, is recovered. Finally, the amorphous at 100 degrees C, that's the glass transition temperature right here, or right here. We're going to see an initial elastic strain, and then because it's not glassy, it's still going to deform plastically. So you're going to see an elastic strain, we'll have some plastic deformation, and then some elastic recovery. Again, this is closer to that curve. So the cross-linked at 180 C is similar to the behavior of the amorphous polystyrene at 100 degrees C. Hardness is another material property. Because hardness is resistance to a permanent indentation in the surface, that's permanent deformation. So it's closely linked to the ductility and brittleness and so on. So if you've got a very hard material, it's going to resist any type of permanent deformation. Means it's going to have probably better wear properties because you won't have, it will be more difficult to remove or change the structure at the surface. Many hardness testing methods use a indenter of a known size or shape or both, and then it measures the indentation made, makes a calculation, and then gives a hardness value. So you can see here that plastics are very low in hardness. Diamond, of course, is very high, and steels run a wide variety depending on their chemical makeup and how they've been produced. How do we measure? There are the Rockwell measurements, there's the Brinell hardness, and Rockwell may use a diamond or a ball and a variety of different loads to measure different materials of quite a variety of hardnesses. The Brinell hardness system is similar in that it uses an indenter and a measurement of that indentation. Here is a chart of the different types of hardness measurement. Brinell, Vickers, Knoop, and Rockwell. They all use some form of indentation and then in a specific load and then a formula for the hardness number. Here are all the different Rockwell scales, A through K. Some using diamonds, some using balls of differing diameters, and they use different loads in kilograms. Now, as indicated before, we can take a material and stretch it beyond its yield strength and then return it without to an unloaded position, and it will then take more stress to bring it to a point of plastic deformation again. So this actually makes it harder to deform. Means that it's hardening. Not all materials are like that. Some will only have a yield strength that is fairly constant, so it has very difficult time hardening. This can be characterized using a fit curve, using true stress, and a hardening exponent with regards to the true strain. And this hardening exponent can indicate how much this material can be hardened or not. Now, these different material properties, whether it's yield stress or elastic modulus or bulk modulus or hardness, these are all, when you look it up on a chart, based on some form of statistical sampling. One wouldn't just take one sample of a 1020 steel and say that the elastic modulus is such and such. One would want to measure many different samples and use statistics to create meaningful data such as the mean or the average and the standard deviation. Standard deviation will give you an indication of how much variation there is. So maybe the steel actually goes from 29 to 30 times 10 to the 6 psi in its elastic modulus. That is an indication that it's not always the same. The standard deviation will give you an idea of how much it varies. The standard deviation is sometimes cumbersome to calculate. It's good to learn how to do it, but it's also very easy to do using standard spreadsheet software. Often, because of this variation, we need to use safety factors. Now, we use safety factors for a variety of other things. It has a lot to do with the design uncertainties. So if we know that we have a static load, our safety factor doesn't have to be as high. But if we have fatigue loading or shock loading, we need to increase that factor of safety by a significant amount. If we have human life or significant possible property damage, if our design fails, then we will have to incorporate, again, a larger factor of safety. So this factor of safety reduces the stress that we should design to. So we take the yield stress or some other failure stress that we've noted, whether it's maybe the ultimate tensile stress, and we divide it by that factor of safety to give us our working stress that we will design to. Sometimes this factor of safety is referred to as FS, not necessarily N. We have an example here of how to calculate or specify a diameter D for a 1045 carbon steel rod using a factor of safety of 5. So the givens are that it's a 1045 plain carbon steel with a yield stress of 310 megapascals and a tensile stress of 565 megapascals. We have a force of 220 kilonewtons. We have to specify the diameter, and in this situation, the original length is not necessary to do our calculation. So we use our working stress formula. We're given the yield stress, we're given the factor of safety, and stress is force over area. So we're given the force, the area is dependent on the diameter. So we take this equation, solve for the diameter of 6.7 centimeters, and we might specify instead a 7 centimeter diameter. In summary, for Chapter 7, we looked at stress and strain and why they were better measures for materials of load and displacement. There are many relationships between stress and strain and the elastic modulus or the shear modulus, the bulk modulus. This elastic behavior is reversible and characterized by the elastic modulus, or for that matter, the shear modulus in torsion. If you need to design to minimize deformation, whether it's a deflection or a angle, then it's best to have a material with a large elastic modulus. Plastic behavior is permanent deformation, and there's a variety of plastic behaviors depending on the material. Some materials are so brittle that they pretty much have zero plastic behavior because they'll fracture before it becomes evident. So those brittle materials, their yield stress becomes their ultimate tensile stress as well. Toughness is the energy needed to break a certain volume of material, and so if you want good toughness, you want to have good area under the curve. So you want to have a high elastic modulus so that the curve shoots up, and then a lot of plastic behavior so that there is a long curve across. Those two things will maximize toughness. Ductility is the opposite of brittleness. Ductility is the ability of a material to strain for a long period of time. So the plastic strain at failure is the measure of ductility. If you have very small strain, you have very small ductility. If you have a very large strain, you have a high ductility. We also subtract the elastic strain to calculate the actual percent elongation. The sample problems shown here are gone into greater detail and are posted on the same site as this is.